PocketQube. We started back in 2013. I printed my first reference cube after seeing Bob Twig's little presentation on what a PocketQube was supposed to be. There was maybe a handful of people even trying to work on these, and then the guy who created it abandoned it. I got my first hardware in 2015, tried to build it, and then they discontinued every piece of hardware I was working on. Created mini cubes in 2018, and Tom Walkinshaw is directly responsible for that. He called me up one day and said, "Hey, we're doing some CubeSat, or these PocketQubes. They're smaller than the CubeSats." I said, "Yeah, I know what they are. You want in?" Like, "What do you mean, do I want in?" Like, "Do you want to fly one?" Like, "I don't know." He said, "Well, come out to the PocketQube workshop." There were about 60 people then. Wow, and I signed up. So we created mini cubes. We rebranded to Quub in 2021. Hire a branding agent if you want to do this permanently. And then we launched Challenger in 2022, which was a 3P PocketQube and suffered failure out the door. We know what the failure is. We fixed it. And then we went ahead and launched on Firefly. Who all watched the first Firefly launch? The one where the payload decided to go sideways while the rocket was trying to go up, and then it did the spin, and then they blew it up. Yeah, we were on that. So we had a reflight, and again, on Firefly, it was a wonderful flight. However, we were in a low orbit. There are folks who know all about that, and it busted us up. This is our office. We started, again, I had a desk. We moved to 15 square meters, then 50 square meters. Now we're 250 square meters in size. We have 10 employees, and we have about 5 contractors that work with us. Okay? So when we talk about Firefly, if you watch the video of the successful launch, the CubeSat going out the door, yeah, we built that. Do I have to hang close to this? Okay, so current status. We have 2 commercial contracts. We have 2 with the United States Air Force. The United States Space Force is one of them now. And we have 3 contracts pending. We currently have a backlog of 9 satellites to build. That's a nice position to be in. So we've built everything. Now, what I'm going to show you here, and I'm sorry for the size of the image, is right here. Okay, we call that Space Hex. Yes, I know Elon's going to sue me. It's a modular iron bird. Okay, does anybody know what an iron bird is? If you're not building one while you're building your satellite, you're going to just hurt yourself. We learned this the hard way. An iron bird is a copy of your satellite on orbit that you can give it commands and fix the things that are going wrong. You'll love it. Trust me. Put it together. But we decided to do something different. Ours is modular. Every sensor set is an individual module that can be snapped in and out, so we can reconfigure the system to match whatever our satellites are. And by the way, our satellite interiors are now also modular, so everything we do in here can be replicated in the satellite, which reduces the manufacturing time. Okay, so let's talk a little bit about machine learning. Who are the AI folks in the room? A couple, okay. So you understand the models and how the models are put together. What we do is a low resource utilization system. So we put together the model, and it's very, very minimal for what we're trying to do. Okay? We have 87 to 93% accuracy out of the box. As we train it even further, it gets more and more accurate. You've heard that there are folks who are doing Earth observation or Internet of Things. We're kind of Earth observation in a slightly different way. We do anomaly detection. We're not interested in what's happening now. We're interested in what's happening over time. So we developed a system to look at whatever is there now, store that, see what's changed, apply our machine learning, and send only the differences down to us. The satellite is making all the decisions. We can, on looking at something going, well, that's a little weird, maybe that's not right, we can then go up to the satellite, request all of its information, and then download that. Okay. Because of this, okay, how many of you are building your own ground station? Okay. May I make a suggestion? Talk to that guy. That's Jacob. Jacob, go ahead and stand up for a second. Jacob runs GroundCom. It's a network of ground stations that you can plug into. You get more than one pass a day. You can get up to 30 passes a day when the system's complete. How's that for data? Okay, so do that. So again, we do image processing using a neuromorphic computer. A neuromorphic computer is something that thinks kind of like a human. So when everything gets very, very complicated, we just go to the neuromorphic computer and say, hey, run this analysis. It makes everything nice, clean, fast, and then we transmit it to the ground. Okay, so let's talk about the hardware. A better picture of our modular iron bird here. The development system is complete. We're not making any more changes. Oh, and by the way, it is scheduled to be open sourced. So everything that we do, you can do. We use a distributed computing system in addition to the neuromorphic computer. Each sensor is its own system. It has its own microcontroller driving it. The microcontroller is like a guard. It takes the information from the sensor and passes it to the CPU, so the CPU is not occupied with worried about the sensors, it's occupied with computing the machine learning. Distributed system. It also allows us to turn off any and all sensors. So if the satellite decides, hey, I'm low on power, it already has a priority list and it shuts the various sensors off until power is restored. Pretty cool system. Nathaniel, our lead, he's our CTO, CRO, Chief Research Officer. He makes things happen. He designed the entire system that we're using today, which is far superior to what I was building. You can see that it's hard to read these, but each one of these modules has a small screen on it, so we can look at what's going on with the sensor in real time, what is transmitting back to the computer. Okay, so model development, as I was mentioning a little earlier, the assumptions are encoded. We send up our model. Here's the fun part. When you're doing this, don't try and image the entire Earth. Pick your areas of interest. Use GPS to bounding box that location and do all of your work there. You'll save processor time. Then you take the information you gather, you chip it, and then you run it through the anomaly detection system. We ingest the images from the camera, first pass using the model, we break it into chips. Those chips are again analyzed using the neuromorphic computer. We store the changes for transmission. Why is this important? I'm a farmer and I want to know what's going on with my crops. Well, why don't we just measure the water content of your crops? And if one section of your field starts failing, we can alert you. I spent 3 years in water quality, for those who remember from me presenting before. That's a fancy term for an engineer who runs around in sewers. Okay? I've seen the infrastructure and what goes on with it. The idea is fix this infrastructure. When there's a flood event, what gets flooded first? The wastewater treatment. What happens to that water is it gets into the drinking water. Okay? Up to 2% of the drinking water that you have right now, that bottle, if you had coffee this morning, I can tell you where your coffee was 4 days ago. Okay? It was somebody else's coffee. Yeah, about 72 hours to cycle water. Okay? That's what gave me the impetus to do this. I wanted to protect a natural resource, water. And so why not build a satellite constellation that can look at the ground, find those anomalies, and oh, look, there's been a sewage leak into the water. This water intake plant should know, send an SMS to them. So again, the machine learning does that and says, this has changed, sends it down. We take a look at it. Yep, it's a problem, and we can immediately send it over the alert system. So this is an idea of what happens when we're talking about anomaly detection. That's a raw scan up there. Can you read anything? When we apply the machine learning, it cleans it up. And so you see all the dots that are there. Some of those are going to be false positives. The rest are actual targets. This is not a regular image. This is synthetic aperture radar designed to fit in a PocketQube. Okay. Anybody want to take a guess at which customer wanted that? Yeah, the Air Force. There's just one problem with all this before I move to the next slide. It doesn't quite fit in the PocketQube. Rats. Now what do we do? I'm not going to CubeSat for this. I'm a PocketQube guy. I'll build CubeSats for you if you want them, but I'm a PocketQube guy through and through. So how do we solve the issue? We solve the issue by making a slight change to the standard. This is our deployer. It's your typical 6P. There are 2 3P satellites, one on each side. But we inverted a couple of things. And so inside this is a 2x3 6P satellite. And the first thing that people are going to say is, well, why didn't you just use a CubeSat? Because we need the surface area, and this is not the same surface area as a CubeSat. That's why. For the sensors and equipment we need, it has to be this big. It also gives you a really, really neat effect. This is Aurora. This is what we've been designing and building. This is the fitment model, but you can see how we have the solar panels and the synthetic aperture radar phased array on the front. I think it's pretty cool. But if we weren't flying this, we could switch over to using 3P, put it in the same deployer, and it will work because the doors are independent of each other. You can see the diagram. Well, you know, it looks so much better on the little screen, and then you put it on the projector and it loses it a little bit. But the difference is that when we use the space between the satellites, keeping all of the standards intact, it's 140 across. I told you this was the least technical presentation. We are launching again on Transporter 8, which is to be determined. We were working with Momentous on this particular flight. We have a long-term contract with them, as well as Firefly and a few others. So we build our satellites in pairs. They're deployed in pairs because they work as a flock. So the constellation is a constellation of flocks of satellites that work in conjunction with one another. Now your PocketQube satellite just went from being a single device to being an array. I think it's pretty cool. But that's me. I want you to decide, all right? So, questions? Did I make my time? Yes. All right. We got 6 minutes for questions. Anybody? Anyone? Yes. What kind of resolution can you get with your SAR detector? The SAR detector goes down to 2 meters per pixel when used in the flock array. Just one satellite on its own gets about 12. Oh, and our optical system goes down to 10 meters per pixel. I can't tell you how that works. Well, I want to, but I can't. Yes?
Does the satellite work on both the sunny side and the dark side? Because I saw the solar panels are only on one side.
The solar panels are fixed for this particular model, but they actually rotate. So it's fully adjustable. We also have a reaction wheel, magnetorquer system for backup. Everything's redundant. And then we also have thrusters from applied ion systems on board. So we have good maneuverability. We have full attitude control. We can do collision avoidance. We also deorbit. All of our satellites are made without any exotic materials. There's no titanium, there's no tungsten, there's nothing like that. We check every material before it goes on the satellite. We guarantee its destruction upon entry with the Earth. 17,500 miles an hour will do that to you. But yeah. Anybody else from up there? And nobody's got any questions. This is a quiet group this year. How many folks, this is your first time being here? Let me ask you that. I hope you're taking away a lot of information, because Alba Orbital and all these folks who have flown can help you avoid some of the mistakes we've made. My first mistake, by the way, when Tom was talking about somebody getting booted off the flight, yeah, that was me. Because the FCC at the last minute denied our license. At that point, no 1P satellite had ever been licensed in the United States. I think it finally happened, but it took 2 years of fighting. 2 years.
What was the reason for denying you?
Because they can't see it. They said that they couldn't see it. I have 14,000 TLEs that says otherwise. I said, yeah, nah. That didn't matter to them. So, any other questions? 3 minutes to spare, Caius. 3 minutes to spare. All right. Thank you, everyone.